Can we start?
Yes.
Okay. So, good morning, everyone, and welcome to this new edition of Water Project Europe on circularity in industrial water. I'm Andrea Rubini, I'm the Director of Operations at Water Europe. Water Europe is the voice of the water sector research and innovation in Europe, and we advocate, we work, we support, we want to achieve a water smart society and economy. The events of today is a clustering initiative bringing together 4 Horizon Europe projects funded under the Project for Planet Public-Private Partnership coordinated by the A.SPIRE Association. The projects are RESURGENCE, Revolution, CORNERSTONE, and MEloDIZER. This event is important because, I mean, the Project for Planet represents also one of the major European industrial ecosystems that supports the transition towards a more circular, resource-efficient, and resilient industry ecosystem. Water Europe is one of the founding members of A.SPIRE, together with 10 major industrial sectors, and over the years, this collaboration has significantly contributed to support ambitious industrial projects of water, energy, materials, and resource recovery, which is really strategic for Europe's sustainability and autonomy in a global climate change, volatile situation, and geopolitical uncertainty. Industrial water is, as you know, I mean, no longer only about treatment and discharge. It's increasingly connected to industrial resilience, circularity, overall competitiveness, and strategic, once again, autonomy of the European Union. And this we are including in the discussion of today, because the project of today presents, I mean, address complementary dimensions of industrial circularity through water recovery, heat recovery, resource recovery, and industrial water use, which help move, I mean, from the linear industrial approach towards a more integrated and circular systems. At the same time, there's also good news because, you know, Horizon Europe is going to be over in a short time, but A.SPIRE, I mean, is currently working on the preparation of a new strategic research and innovation agenda for the next framework program, FP10. And these are in order to help to ensure continuous support to the key industrial transition Europe will need in the coming years across water, energy, materials, and resources. So the end is today is about contributing to a broad strategic discussion of the future of European industry and industrial sustainability. A lot of thanks, I mean, tons of thanks to all the project speakers and the participants joined today. And now I leave the floor to Christophe Prief, who is the head of the International Affairs and the EU at the Norwegian Center of Expertise, Sustainable Process Industry, and chair of the working group for materials, circularity, and efficiency at A.SPIRE Project for Planet. Thank you so much. Christophe, the floor is yours.
Thank you, Andrea, for the invitation, and hello, everyone. And thanks for the opportunity to say a few words. Well, the way at the moment it seems to be we're moving ahead. I mean, first of all, I think I'm sort of preaching to the converted, of course, but yes, industrial resilience, but also water is such a concerning issue for other parts of society that resilience has to be sort of understood in a wider context. So I think looking at it from a circularity perspective, for processes for planet or processing industries, I mean, water being a global issue, of course, or issue of global concern, it's also a local issue. Like the water treatment, water management is dependent on the local conditions. What are the pressure points, the context of the industries, the sectors. So there is a lot of variety there. And I think therefore also it's closely linked to industrial symbiosis and local sort of industrial developments. We're not going to, presumably, hopefully we do not end up in a position where we really sort of have to transport water with logistics any more than we're already doing. But of course also it means also increasing competition for water in those locations. So we're already seeing projects, huge investments just to sort of, not just, but to make water cooling water systems, for example, circular, because we cannot, or those industries cannot tap more groundwater. They cannot, without side effects that are sort of not wanted. So I think increasingly it will be linked in the future to license to operate and to avoid local conflicts. Also, what it's we're talking about big investments in the end of the day, but also we need to therefore be mindful. Like there will not be, probably not, like one investment for water treatment, one for energy recovery, right? One for nutrient recovery. So I think these issues, they will need to be looked at integrated in one sort of recovery system, or find your own words, I guess, for it. But these issues are interconnected. Instead of having to invest in solution A, B, C, and D, we will need to probably look at sort of more integrated solutions to make them, make them fly, basically, to have a balance between the cost of the investment and the operational costs in the end. Yeah, so I think that's where we are at the moment. What Andrea mentioned, we're just starting the process of a new research innovation agenda in the partnership, and I do not see that innovation agenda sort of working without water as a critical part of that, because of the things I just said. So we're looking forward to the input. I mean, the process is that we gather knowledge. That's what we're starting now. We gather knowledge and input, and then we digest it into an innovation agenda. So the outcome will be only as good as the input that we're provided by you experts in the end of the day. So looking forward to your contributions, Andrea, on the way ahead, and looking forward to hearing more.
Thank you so much, Christoph. Thanks a lot. Thanks for your words. I mean, yes, you're right. I mean, we cannot go ahead without considering water as an essential factor for sustainability. But now, I mean, geopolitical tensions, I mean, also tell us that we need to be careful about resources and any factor, I mean, that can contribute to stabilize and to maintain stable, I mean, our society from the economic, from the social point of view, and political as well. Thank you so much for your contribution. I also look forward to work together with you, I mean, in the ASPIRE, I mean, the Strategic Research and Innovation Agenda in favor of the next FP10. So now, I mean, we have a keynote from the European Commission, and I welcome Eleftherios Manousis. Eleftherios works, I mean, at the European Health and Digital Accelerating Agency as a project advisor in the unit ADEA B3 Industry Advanced Materials. Eleftherios, thank you so much for joining us today, and please take the floor.
Thank you very much, Andrea, and happy to be with you. To be honest, I will not share my presentation with you. It's a 22 slides presentation, and most probably you will get it after the webinar as an attached file from the coordinators of this event. So the keynote here is double. The first part of my keynote is the organizational and financial components of this, let's say, effort. And the second one is the topic related and the project related one. So briefly, I will go through my slides without, to be honest, referring to details, because the time is limited. So as Andrea said, I'm from the European Commission, from the Health and Digital Executive Agency, working with the industry unit and with industrial projects. I'm also the project advisor for all these three water relevant projects, Cornerstone, Resurgence, and Revolution. The first part of the keynote, which is about the programming the programs that we manage. You know that we manage health, food, digital, industry, and space. We are in the industry here, and we are in advanced materials. The budget that we have is around 20 billion for this working program period, and particularly for digital industry and space, we have 5.6 billion plus 0.5 billion, which is under the Next Generation EU. I think some of the projects are also financed by this funding program. The role of HADEA is in the entire project life cycle, from the call for proposals up to the exploitation and dissemination of results, including proposal submissions, evaluation, grant agreements preparation and signing, and of course the scientific and financial project monitoring, which is the most critical one. Then I will move to very briefly to the need for periodic reports that we need from the three projects that I mentioned. Clear periodic reports with what you did, what did you achieve, what problems did you encounter, and what deviations did you have. Then the payments based on your periodic reporting and sometimes amendments. And I will stick now to three very relevant issues that we would like to highlight. The first one is visibility. I was happy to see that even the agenda was referring to the Article 17 funded by the European Union. Thank you very much for the organizers for this. Then dissemination and exploitation. Second pillar of the project is the Open Research Europe, the open access for peer-reviewed publishing platform for scientific articles, and the importance to publish in the Open Research Europe platform. And with this, I would like now to move to my specific key point for the particular topic. You know that the three projects, Cornerstone, Revolution, and Resurgence, are part of a topic called sustainable and efficient industrial water consumption through energy and solute recovery. So this is a complex topic, very ambitious, because it's not only about water recovery, but also about energy. As far as I saw it, is heat, the way that you will approach it today, and solute recovery. As far as I saw, it's you call it resource recovery, which is equivalent to the solute recovery. So you see that it is an ambitious topic with particular interest for both processes for planet partnership, and I would like to specify it more to energy intensive industries. This is exactly where we have our feedback to policy, to the European Commission Research and Development Directorate General, and that's why this topic and these three projects are interesting and very relevant. I will now move to much more specific key points, which are, for me, it is, but also for the topic, is the industrial water circularity that involves recovering water, heat, energy, and resources to reduce waste and environmental impact. Also, transitioning from linear to circular water management that will strengthen the resilience and sustainability in industries. This shift requires technological, operational, economic, and regulatory changes. And of course, collaboration across sectors, which is essential to overcome common barriers and share best practices. And referring to the feedback to policy, I would say that policies must support innovation and investment in circular water solutions. And last but not least, citizens and businesses will contribute by adopting these water efficient practices and supporting sustainable initiatives. But all these are not only wishes, because we have to break down in details, and we have, I would say, in this topic, we have four pillars. So the first one is the wastewater discharge. Second one is industries with high wastewater discharge, the energy intensive industries that will process and their wastewater volumes, particularly industries such as pulp and paper, steel, and chemicals. And the third pillar could be the targets for wastewater reuse. And here we have the ability of the Process for Planet initiative to demonstrate the potential for reusing 90% of wastewater by 2030. Achieving this target could involve combining existing and novel water treatment technologies, implementing process identification and energy recovery, utilizing excess heat, and integrated processes with separation systems to reduce water and energy consumption. Last but not least, again, what you call here resource recovery. I saw it that two of the projects will refer to this. If not mistaken, all projects will refer to the resource recovery. The valorization of industrial wastewater, because it contains significant amounts of valuable substances such as organic matter, salts, phosphates. However, these substances are not always optimally utilized. Improving the valorization of these substances could provide additional benefits beyond wastewater reduction. And this is one of the targets and the objectives of the three projects that we'll present it today. That was all, but I would like, as a final keynote message, to ask you to become an independent expert. I'm sure that in this webinar we have skillful colleagues, and as the European Commission is continuously asking for new experts, we would like you to check the communication portal and check the funding and tenders portal, sorry, to register yourself, if not done already, as a new expert. This will give you the opportunity to read excellent proposals during the evaluations, or to network with fellows, and sometimes to be the project monitoring for the projects that we implement. So we need people from the academia, from the private sector, innovation agencies, and also but from local and national authorities and agencies. So everybody is welcome, of course, with a relevant expertise, and the link will be in one of my slides. If not already registered, please feel free to do so. Stay in touch with HEDEA and with the European Commission. And I would like to give the floor back to Andrea, or I don't know if it's Isabella, for the continuation of this webinar. Thank you very much. Any questions at the relevant part of this event, feel free to ask. Thank you very much. Bye.
Thank you so much, Therios. Thank you so much. And yes, I mean, I myself now, I pass, the floor to Isabella for the continuation of the event. Thank you so much once again.
After the opening contribution, we turn now to the project session. And I'm pleased to introduce Shufei Yang, Senior Researcher at SETI Technological Center. Shufei coordinates the RESURGENCE project, which aims to support the circularity in industrial water management. Shufei, the floor is yours.
Thank you, Isabella. I'm going to show the presentation. Could you see the presentation?
Yes.
Yes, okay. Like Isabella said, I'm the project leader of RESURGENCE. The complete name of our project is Industrial Water Circularity, Reuse, Resource Recovery, and Energy Efficiency for Greener Digitized EU Processes. I'll just give a quick project overview for those who are not familiar with our project. We are a four-year project coordinated by SETI Technological Center together with 70 partners and 2 affiliated entities over Europe, and a university from Pakistan and industry from Turkey. Our main objective is to transform European process industries into wastewater resource recovery facilities. This means moving beyond the pollution control to resource valorization, supporting Europeans' 2050 goals, climate neutrality, circularity, and competitiveness. To do this, we are developing modular and flexible treatments and digital technologies to enable the recovery of water, energy, and valuable resources. Well, our strategic framework is called Seeds of Hubs for Circularity. The concept is that circularity grows step by step. First, we plant the seeds, which are demonstrating individual circular solutions. And then these seeds grow into pilot plants, which are integrated industrial ecosystems where different solutions start to connect. And finally, these pilots mature into hubs for circularity. While this framework aims to establish the foundation for future industrial symbiosis or even industrial urban symbiosis to enable industries as enabler of the green and digital transition. And to implement this concept, resurgence methodology is developed in 4 main stages. The first one is the research of innovative technologies, including water treatment technologies and digital tools. The second step is the integration of technologies, design, construction, and validation of the pilot plants in 3 industrial case studies. And the third step is the promotion of the strategy of Seeds for Circularity, including an industrial urban symbiosis case. And the last step is the maximization of replicability and scalability. In the project, we have 4 case studies. The first one is a pulp and paper industry located in Portugal. The second one is a chemical industry in Turkey. And the third one is a steel industry located in Poland. The last one is the urban industrial symbiosis located in Spain. Today, we are going to focus on the case study of chemical and steel industry. Well, as mentioned by Eleftherios, in all the 3 sister projects, we recover water, resource, and energy. But in today's presentation, we will focus on the water and resource recovery of these 2 industries. For water recovery, we have studied membrane distillation, biomimetic reverse and forward osmosis membranes. And for resource recovery, for the chemical industry case, we have studied the latex recovery from the wastewater through ultrafiltration. And for the steel industry, we have investigated the phosphate and magnesium recovery through electrical chemical processes and through adsorption. And today we are going to focus on membrane distillation, latex recovery, and electrochemical processes. Starting with water recovery, I'll leave the floor to my colleague in the project, Dr. André Torres Pinto. He's a researcher in University of Porto, specialized in photoelectrocatalytic carbon-based systems for wastewater treatment.
So,
Please.
hi, good morning. So I'm going to speak about the work that we're developing here at the University of Porto regarding the water recovery in the Resurgence project. So starting with, I'm going to speak a little bit about membrane distillation. So what is this process about? Essentially, on the scheme that I show here on the left, there are 2 currents of effluents. One hotter side with a feed that is the retentate side, which is highly contaminated streams, usually from industry. And on the other side, we have the cold side called the permeate, which where we will obtain the clean water effluent. As you can see, please, Shafay, there is an interface between the two sides, which is the membrane, and we have the pores that are identified by the arrows, from which, by thermal induced process, we have the water vapor generation that passes through these pores and goes to the permeate side to obtain the water. So in the next, I have some, so after the separation process, what we obtain is that on the feed side, on the retentate, we have very salt and organic rich retentate, which leads to the concentration of these waters. But on the other side, on the permeate, we obtain the clean water from these high contaminated streams. So on the next slide, I will present the setup that we use for the direct contact membrane distillation. Direct contact is because the membrane has no vacancies and we have direct contact between both retentate and permeate. We operate with this membrane module that I show here, which has an effective contact area of 70 squared centimeters, which is relatively high for lab scale operation. The permeate side is kept at 20 degrees Celsius, which is very easy to maintain in lab scale. However, to have a more efficient process, we have to perform some preliminary optimization, and we do so using distilled water. And on the first graph that I show here, I have the permeate flux, which is what we want to optimize, versus the flow rate on both sides of the membrane. Increasing from 100 to 100 milliliter per minute, we see that we reach a plateau at around 500 milliliter per minute for this setup in specific, and we have the higher permeate flux for this value. In terms of temperature difference, which is what drives this separation process, we see that increasing the temperature, which is shown here on the x-axis as the differential of pressure, we see that the higher pressures, they are still relatively low compared to other filtration systems. But in this case, what interests us is the difference between both sides of the membrane. For the 37 kPa, we have a retentate side of 80 degrees Celsius, which we obtain the higher permeate flux. However, this has to be taken into consideration because at higher temperatures, if the retentate stream has volatile organic compounds, they will also be transformed to the gas phase and pass through the membrane. And so therefore, the next studies that we show, it's going to be for the 60 degrees, so not the best conditions, but we had to choose a compromise. So on the next slide, I show some preliminary results using the water that we obtained from the different case studies. So on this graph, I show the interval flux for two waters from the chemical industry, which is the OK water, and then one water from the steel industry, the casting wastewater, the CCW. So as we can see over time, we generally operate for 3 hours and we obtain very stable interval fluxes, especially comparing the industrial wastewaters to the distilled water stream. We see that the fluxes were all about 18 kilograms per square meter per hour, which is highly stable, and this leads us to believe that the membrane is not being saturated or there is no pore blockage over this time. Then, obviously, I want to speak about water recovery, which is the main topic of this part. And we can see that after only 3 hours of operation, we recovered water as high as 42%, especially for the steel industry. This one is because they have very low organic content and it's mostly inorganic salts, which remain retained in the retentate side very easily through this process. And compared to distilled water, obviously the results are very similar because this process in such a short time works pretty well. Finally, it's easy to analyze the retentate, and we see that over 3 hours of operation, we have a concentration of the dissolved organic carbon on the retentate side, which is more or less 1.5, 1.6 concentration factor, which is in parallel with the water recovery that we obtain. Then, in the next slide, I show some specific results for the case study of the chemical industry wastewater. The partner that we have in RESURGENCE has some criteria that they have for water reuse. In specific, the pH values are very important for them, And through this separation process, we kept the pH around 7, which is what the partner wanted, but also they wanted to study the hardness of the water. And so we were analyzing both calcium and magnesium ions on the retentate side for the two effluents that they sent us. And as we can see on these results here, in 3 hours, we have the concentration of these ions on the retentate side, and this goes in parallel with the water recovery that we obtained. The permeate side had insignificant water, and we can see that we are concentrating these ions on the retentate side, which might be useful for some resource valorization in the future. And finally, we have to always analyze the membrane after these studies, and we can see that after operation with distilled water, the membrane keeps its fresh appearance, and after the wastewaters, there is some fouling and scaling on the surface of the membrane. However, as I showed, the interval flux was kept the same, but if we analyze ultraviolet visible absorbance, we see that there is, in fact, some deposition on the membrane, but still the spent membranes can be reused over time. So that's it for now, and thank you. I'll pass the word now to Shuefei.
Thank you, Andre. I'll continue with resource recovery in the two industries, starting from latex recovery. Well, the wastewater from chemical industry contains latex particles and mixed polymers and dissolved organics. They are using a ultrafiltration system which suffers from fouling and insufficient latex recovery efficiency. So our objective is to improve the latex recovery with ultrafiltration. Firstly, we tested the membrane rotation to increase the shear at the membrane surface and reduce fouling. The process diagram is shown here. A rotatable component was added to the membrane module, allowing the membrane itself to rotate during the filtration. As mentioned, the initial approach was carried out using rotating ultrafiltration with synthetic wastewater containing 1% latex. The water recovery reached 80%, and the latex was concentrated by a factor around 3. However, the permeability was low for ultrafiltration and declined rapidly. Severe fouling was still observed on the membrane surface. And considering that real wastewater would be more complex to treat, coagulation pretreatment using Tintosan, a natural bio-based coagulant, was tested. In this new approach, real wastewater was used to properly assess the coagulation performance. And after the dosage optimization, Tintosan coagulation was applied, leading to the formation of larger flux. And ultrafiltration was then tested without membrane rotation to avoid additional energy consumption. A clear permeate and latex concentrated retentant were obtained. And in this case, water recovery improved to 95%, while the latex was concentrated by more than 10 times, and the permeability increased by a factor of 2.4. And in the photo, the latex recovered with Tintosan coagulation before ultrafiltration, and the latex recovered without coagulation are shown. With Tintosan coagulation resulted in a more concentrated and stable latex recovery. And the FTR analysis was performed to confirm the composition of the latex recovered and with a commercial concentrated latex. And the results confirmed the recovery of latex like polymeric compounds from chemical industry wastewater. So from this step, we could confirm that coagulation together with ultrafiltration enabled higher recovery and improved the concentration of valuable polymeric material. And then I'll leave the floor to my colleague, Eugenia Quiros. She's a senior researcher at CEDIM Technological Center within the eco-biotechnologies area. She specializes in electrical chemical technologies and MOFs synthesis for water and air treatments. Please, Eugenia.
Thank you, Shofei. So in this part of the presentation, we are focused on the phosphate and magnesium recovery from steel industry. So the steel industry generates also large volumes of wastewaters with high concentration of salts and dissolved ions, in particular in resurgence projects. We observe the phosphate and magnesium due to the both are critical raw materials. And the recovery of these compounds supports also the circularity, the water reuse, and the resource valorization. In this project, we focus on electrodialysis technology due to its an efficient technology for selective ion separation and resource recovery. This technology is an electrochemical based technology, also based in membrane separation, and this technology allows us to separate also the phosphate or the magnesium ion from other ion present in the wastewater. The principal advantage of the electrodialysis is, as I said, the selective ion recovery, low chemical and low energy consumption, also is suitable for concentrated streams and compatible with circular treatment trains. In this project, we are focused on the modification of electrodialysis membrane by metal organic frameworks because these materials enhance selectivity and improve recovery performance. Thank you. So, which are the metal organic frameworks? These materials are a class of porous materials composed by metal ions and organic linkers, which form different porous and different structures. This variability allows us to obtain more than 10,000 of compounds and present also high selectivity, high specific surface area, high stability, in particular to high stability of temperature and also of the presence of contaminants, and also multiple applications. However, these materials are difficult to scale up, so are still at low TRL. So in the next slide, we choose one MOF, which is UEO66 doped with an amine, to dope nylon commercial membranes for phosphate recovery by electrodialysis technology. We optimize the synthesis by hydrothermal method, and we obtain the various membrane, around 20 membranes, with a size of 120 square centimeter. And we observed that the membrane characteristics, their structural and technical characteristics are maintained. In particular, the resistance, which are lower than 1 ohm per square centimeter. We used in the next slide this membrane in our setup in the electrodialysis setup, which is composed by 12 MOF-based membranes and also 11 commercial membranes. This electrodialysis cell also is composed by 2 electrodes, and we have two compartments: the dilute compartment, which is filled with distilled water, and the concentrate compartment, which is filled with a concentrate solution, which in this case is the wastewater. We applied the electrodialysis for 1 hour by 15 cycles, as you can observe in the scheme. In the first step, we apply 60 seconds with no current for stabilization, and then we applied 10 milliampere per square centimeter over 1 hour, which is the electrodialysis step, and then repeat it again. We obtained a stabilization of the potential signal after 6 hours, which is maintained at 2 volts, and we make sample points every hour, also in the concentrated stream and the diluted stream. We analyze these samples by ICP mass spectrometry and ion chromatography, and we observed that in the diluted compartment, more than 95% of recovery of phosphate with a selectivity greater than 5 to 1 compared to other ions. If you go to other, for magnesium recovery, we try to implement this technology, the electrodialysis, but the results are not very good. So we changed the technology and we applied electrodeposition, which is also electrochemical technology, but in this case, the current and the potential is applied between two electrodes, and the magnesium in this case is deposited on one of the electrodes. So we applied 50 milliamperes during 24 hours, and as you can observe in the XRD and also in the image, we obtain a white solid, which is magnesium doped calcite, which implies a 50% of recovery of magnesium and calcium from the wastewater. So finally, in the Resurgence team, we propose a final strategy which implies two steps for phosphate and magnesium recovery. In the first step, we apply the electrodeposition for the magnesium doped calcite recovery. This step allows us to also concentrate the phosphate, which enhance also the electrodialysis technology in the second step. And finally, we obtain the wastewater without these two critical raw materials, but probably this wastewater is necessary to be treated by other wastewater or water treatment technologies. So thank you.
That's all for from Resurgence side. I'll pass the word back to Isabella.
So we continue with Lidia Fernandez Rojo, Senior Project Manager at the Setaqua Technology Center. Lidia coordinates the Revolution project, which focuses on advancing circular solutions for industrial water management. Lidia, the floor is yours.
Thank you, Isabella. Can you see my screen properly?
Yes.
Perfect. Good morning, everyone. I'm Lidia Fernandez, and I will do a general approach of the Revolution project, which is entitled A Revolutionary Approach for Maximizing Process Water Reuse and Resource Recovery through a Smart, Circular, and Integrated Solution. So, water challenges is the driver for the Revolution project. So water scarcity is currently affecting 20% of Europe's territory, which represents 30% of the population yearly. And water stress is expected to increase due to climate change, demanding efficient management of existing water resources. In addition to that, 40% of water extraction goes to industry, which represents a high consumption of fresh water. They also deal with managing complex effluents to treat, and also with the increasing cost of these treatments. So to solve these problems, here we propose to implement a water reuse and zero liquid discharge strategies to increase water saving, resource recovery, and environmental compliance. However, nowadays it currently implies high cost, high energy consumption, and technical complexity, which still requires some innovation. In this context is where Revolution was born, so to give a solution to all these problems. Revolution project started at the beginning of 2024 and will finish at the end of next year, and it's composed of 20 partners from 9 different countries with a budget of almost 11 million euros. Here you can have a look at the whole consortium. So the project is coordinated by Setaqua, but we also have other research technological organizations. We have 4 main industries involved in the project, which are Repsol, Celsa, Bloom, and Felix Scholler. We have also digital partners like CERT, IDNR, and in some of the Imperial College London or Vieda. And then we have also transversal partners that are dedicated to the communication and exploitation strategies of the project. We have 4 main key objectives. The first one is to design the wastewater treatment drains for water reuse, solute recovery, and heat reuse, as the other 2 sister projects, and also ensure complete removal of hazardous substances. Then our second objective is to develop novel membrane materials and define how they will be integrated in terms of functionalization and configuration to maximize the process efficiency in the treatment drains. And then we are developing a smart digital tool for decision support, risk management, and process optimization. And the final objective is to demonstrate this digital tool in the 4 industrial sites. Our demonstration sites involve 4 different energy-intensive industries, which are the petrochemical, the bio-based, the steel, and pulp and paper. For the petrochemical, we have Repsol, which is located in Spain. Then bio-based, we have Bloom, together working together with Vito, which are located in Bloom is located in Switzerland. Then for the steel, we have the Telsa that works with the mentoring of UPC in Spain. And then we have Felix Scholler, which is located in Germany and works closely with Fraunhofer. So in all of the demo cases, we have the objective of recover more than 90% of water reuse, then recover at least 50% of heat recovery. In some of the other cases, it's even higher. And then to recover different resources or compounds, depending on each industry. For example, for the petrochemical and steel, we'll aim to recover sodium hydroxide, hydrochloric acid, and ammonia. But then for pulp and paper, they want to recover filler recoveries, with which are one of their production compounds. And then in Bloom, their target are the different organic fractions. With that, I will give the floor first to my colleague Sara Salvador from Vito, which will give you more details about the resource recovery in this demo case in the bio-based. And then afterwards, I will give the floor to Sigurd Sano, who will explain how heat recovery is being implemented in this project in the 4 different sites. Thank you.
So thank you, Lydia, for the introduction. I think you can all see my screen. No?
Yes.
Okay, for some reason I minimize it so I cannot see it myself. Sorry, one moment. Sorry, I'm having a little problem. Just one moment. Okay, it should be there now.
Yes, it is.
Yes, sorry for the inconvenience. So thank you, Lydia, for the introduction. And I will now focus on one of the demo cases within Revolution, which is the Bloom Biorenewables case study in the bio-based chemical sector, as already introduced by Lydia as well. So in this case, the objective is not only wastewater treatment, but also evaluating how water and dissolved compounds can potentially be recovered and reused in a more circular way. So Bloom Biorenewables is a spin-off from EPFL in Switzerland, and they are working on the valorization of lignocellulosic biomass into added value chemical products. These processes are highly water intensive, and they generate process streams containing dissolved salts, sugars, and some other organic compounds. So within the project, we are investigating how these streams can be treated and integrated into more circular water management strategies, as the 3 projects today, basically. So within the project, the selected demonstration case focuses on the cellulose wash stream generated during the process. This stream contains mostly salts, sugars, and some residual organic solvents, making it a very interesting case, at the same time complex, of course, for evaluating the different recovery strategies. So the objective is to investigate how membrane technology can separate different compounds and enable different recovery possibilities. And across the different routes that we are exploring, we aim at getting very high water recovery, as already explained, and minimize the residual waste streams. And in this specific case, the water recovery can be potentially reintroduced in the same process for the cellulose washing. So that would make it a very nice closed loop system. So to investigate the different recovery possibilities that we have, we are evaluating different membrane technologies, mostly pressure-driven filtration like nanofiltration and reverse osmosis, and also membrane distillation for the separation and concentration of the different compounds. Depending on different membrane behaviors and recovery objectives, we are considering different process configurations. And in all these processes, we are working with commercial membranes, but also with membranes developed within the consortium. And I have to highlight that we are also using especially ceramic membranes, since for this case specifically, they present very high chemical stability, which is needed when you have some organic solvents in your stream. So we have conducted so far a very extensive experimental membrane screening, and I'm not going to go into details, but we have identified different possibilities for reuse, depending on the separation behavior of the membranes. So one possible route focuses on producing a sugar-enriched stream together with water. Another pathway targets salt concentration and recovery, although higher recoveries and concentrations, as you know, increases scaling risks and operational limitations. And intermediate configurations are also possible, generating mixed streams containing both inorganic salts and some dissolved organics. So at the moment, we are actually discussing with Bloom and looking in detail at the different strategies to evaluate which approach makes the most sense to them from a technical point of view, but also from an application perspective. So overall, the results show that the different membrane behaviors can lead to different trade-offs between the recovery route that we can follow, stream purity, and process operability. So beyond the different routes that we are still investigating, we came up with important technical observations. So first, the results indicate that we have a strong potential for high water reuse, and basically the required process configuration depends a bit on the targeted reuse quality. In parallel, the potential recovery of the dissolved compounds also depend on whether these fractions have a realistic reuse opportunities and can be recovered in a technical feasible way for the company. when we work at high recoveries, operational aspects such as scaling and flux limitations become increasingly important. In addition, during membrane distillation, residual organic solvents may transfer into the distillate. So solvents need to be managed quite well. And this was already mentioned by Andre before. And overall, the work shows that resource recovery strategies must remain stable and practical to operate under industrial conditions. So the work is now progressing from laboratory testing towards integrated pilot validation. This will happen somewhere in the autumn at Bloom's site. And as already mentioned, we have tested a lot of membranes, commercial and in-house developed membranes in terms of selectivity, flux behavior, and recovery potential. Now we are doing some extra testing at longer term with small modules still at laboratory scale, but we are trying to assess in a better way the performance of these membranes. And in the coming months, still prior to the pilot, we will still perform some combined techniques at laboratory scale to de-risk the pilot implementation. So to conclude, the work demonstrates the potential of hybrid membrane systems to enable both water reuse and resource recovery in complex bio-based streams. At the same time, the results highlight that recovery route must be balanced with technical feasibility and longer-term process operability. The project is now progressing towards integrated pilot scale validation as the next step towards industrial implementation. And overall, the work is supporting the transition from conventional wastewater treatment to a more circular water and resource management in the bio-based industry. So thank you very much for your attention.
Please, Sigurd, the floor is yours.
Thank you. So can you see this? Is it in, let's see now.
Is it
It's okay?
It's not in the presentation mode. Okay, now it's fine.
Oh, okay, thank you. So just let me things away. So yeah, hello. So I'm going to talk about the thermal energy analysis and excess heat recovery in the Revolution project. This is the work of Syntef Energy Research. So the first part is on excess heat analysis. You will see how composite curves will be used to identify the excess heat potential in these industrial sites we are looking at. So that deals with the cooling demand and the heat demand and the pinch temperature. And we will look at some of the results for the demo cases. And then after that, I'll go to the closed loop approach. We'll consider the basic vacuum membrane distillation setup, and then we'll see how heat recovery can be utilized by heat upgrade using heat pumps. So composite curves. Well, if you look at the left figure here, we see 3 different streams at different temperatures from beginning temperature to a target temperature. And given that, this is a way to identify the streams in terms of their energy or heat potential. This is associated with changes in the enthalpy, where C dots here are the heat capacity flow rates. And what you observe here is that these curves, they overlap in the temperature ranges. So the composite curves in the right figure, you divide into the intervals and you sum up the contributions from the different streams. So that is the composite curve. So basically what it tells us is how much heat is available for a given site, and also at what temperature level, and this will be important. So here is an example. Let's say this is the composite curve from a given site, the red curve here, and then the blue curve represents the heat demand of the membrane that we are using. So what is critical here is the pinch temperature. It's say it's about 5 Kelvin. This is the minimum temperature that is necessary, temperature difference between the supply and demand. So this blue curve, the length of it represents the total heat demand, and the temperature along the vertical axis represents at what level. So basically the width of this, if you look at the red curve above the blue line, that represents the total heat available by direct use. So that's the point. So what we see here also from that figure is that not all of the total heat available for the site is not available for direct use. So we have considered 3 of these industrial cases in the project. The paper Felix Scheller did not have any relevant streams for direct use, so that's why we considered Repsol, Celsa, and Bloom. So for Repsol, you see that there is a large excess heat potential, and some heat of that is supported by the vacuum membrane distillation, whereas most of it can be utilized using another method with a direct contact membrane distillation, which is more like a heat exchanger, whereas in the vacuum membrane distillation, you use a vacuum pump. For Celsa, there is a large potential, but none of it can be used directly by vacuum membrane distillation, but almost half of it by direct contact membrane distillation. Bloom has smaller values, but some of it, or most of it, actually can be used by direct contact membrane distillation. Yeah, you also see the difference here. So there's a pros and cons between the VMD and the CMDs. VMD has a smaller temperature range for its use. So let's look then at the normal setup, vacuum membrane distillation. So we have heat input here at 85 degrees. So that requires heating, 85 degrees. And there is a cooling demand as well. So the VMD, it needs both heat input and cooling. And this actually opens up the possibility to use a heat pump here to upgrade the cooling demand or the temperature from the cooling to heat. So this is the setup. Vacuum is here applied on the permeate side, and water evaporates outside of the membrane. And this is what drives the process. So now, if we combine with a heat pump, we see here that the heat pump extracts the heat from the cooling side, and then this is re-injected on the heating side. So the heat pump, it connects the cooling demand with the heating demand, and therefore we reduces the overall energy demand and a separate need for heating and cooling. So this is the benefit of this setup. So finally, we have, so the idea in the project is to combine these two setup. So here on the left side, you see the setup of the membrane distillation done by Fraunhofer. And on the right-hand side, you see the heat pump configuration developed at SINTEP. So the red loop here represents the heating side. So heat from the heat pump condenser is supplied to the membrane feed side. And the blue line here represents the cooling side, where heat is extracted from the MD cooling side and supplied to the heat pump evaporator. So this is a work in progress. Right now, we are still waiting for heat exchanger, but very shortly, we will then configure and set up this heat pump, and we will connect these two systems. So summary, excess heat is available at several industrial sites and can support future membrane distillation. The usefulness of this methodology depends strongly on temperature level, quantity, and also on practical integration. Composite curves are an effective tool for comparing available excess heat and thermal demand of membrane distillation, and to identify the potential for direct use. And some heat streams here can be used directly, while lower temperature streams require heat pumps to become useful for membrane distillation in the water reuse or resource recovery. So thank you. That was it.
The following speaker is Cześć Jensen, Associate Professor at Aalborg University. Cześć coordinates the Cornerstone project, which focuses on water, energy, and solute recovery from industrial water streams. Cześć, the floor is yours.
Thank you, Isabella, and I hope you can see my screen.
Yes.
So I will just give a brief overview of the Cornerstone project. So the long title is Combined Technologies for Water, Energy, and Solute Recovery from Industrial Process Streams. So like the other sister projects that we just heard about, we are focusing not only on water but also on the energy and solute recovery. And just some facts and figures. We are 16 partners from 8 countries, and it's coordinated by Aalborg University. It has a duration of 48 months, so we are more than half now in the project period. And then we focus on different treatment modules in 3 different case studies. And here you can see our partners. We have a very nice consortium, and we are 6 large enterprises. We are 5 research and technology organizations, 1 SME, and then 3 universities. And we are located in different countries in Europe. And then just an overview of our concept. As I just talked about, we are using different treatment modules. It's mainly based on membrane processes, but also on a heat exchanger for heat recovery. So that is our component 1. Then we also have a component on digitalization, where we integrate different sensors, we control it with and optimize with AI. And then we are also doing digital twins for 2 case studies. And in component 3, we are focused on demonstrating this integrated system, both in the steel industry, in the pulp and paper industry, and in the chemical industry. So again, similar to what the other sister projects they showed. And then we also have a 4th component, what we call the transversal strategies, where we have the sustainability assessment and social assessment. Then we have an exploitation toolbox, and I think that is also very important to highlight from the Cornerstone project, that we have some decision support tools in our project, not only for water, but also for energy and the resources. So how does industry actually take the decisions to recover these valuable resources? And then, of course, also a part is the communication and dissemination. the overall objective of our project is to achieve circular economy. So again, aligned with what Eleftherios and the speakers before have told about, through the recycling and reusing of the resources in the industrial water and wastewater streams. Again, as mentioned before, we have 3 demonstration sites. So one case study is within the chemical industry, where we focus on chemical energy and water recovery, and that is based in at Covestro, and we will hear more about that in a moment. And then we have also another case study in the steel industry, where we have focus on HKM, but our focus is on energy, water, and asset recovery, and that we will also talk about later on in this event. And then the third case study is on pulp and paper industry, where we have Essity as a company, and here we focus on energy, water, acid, and sulfate compounds recovery, so minerals recovery from this case study. But we will not talk about this case study today. But of course, if any of the participants are interested, we are always interested to inform you more about this case study as well. So this was a very brief overview of the Cornerstone project, and by that I will just say thanks for this part, and then I will give the word to Christoph Blöcker from Covestro Deutschland. And Christoph, he is the head of infrastructure, processes, HYCO, and materials corrosion. And Christoph and his group is leading the case study within the chemical industry in the Cornerstone project. So I will just give the word to you, Christoph. So please.
Yeah, thanks, Chesna. Now we are talking about the chemical industry case study in the Cornerstone project. And now what's chemical industry about? I will present shortly. Covestro is a classical chemical industry. So global presence, global production sites. You see here the world scale sites, which have an integrated sites. In total, we have 46 production sites, about turnover 30 billion. Our chemistry is focused around polycarbonates and polyurethanes. However, what we are doing here is quite representative in general for the chemical industry. Our customers is automotive, it's building, it's furniture, it's electronics, so quite a variety, which means what we are doing is really representative and applicable to many more sites and industries. And we talked a lot about heat and energy recovery from water in the talk before in terms of heat. In our case, we also want to gain energy from water, from the wastewater, but we want to gain the energy, the chemical energy in our waste and wastewater. I mean, what is wastewater? It's some water with organics, etc. It can be either wastewater or even classified as waste. And no matter what we do with it, whether we give it to an aerobic treatment plant or whether we give it to an incineration plant, we convert the organics to CO2. We spend energy for that. And in the end, we spend energy and create emissions. However, we would like to valorize the organic energy in the waste and wastewater. And to give you a bit an idea on scale on that, what you will find here now is 2 slides on a balance, on a normalized balance. So if you consider all the organics, so in wastewater terms, we call it COD or TOC. If you convert it into chemical energy, meaning you simply take the heat value of this organics, if you're, for example, a solvent or something, it has a certain heat value. And if you take that as 1, so this is a chemical energy, the blue one, which is there, so it's present. If you incinerate it, and the example here is a liquid waste with 5% organics, about 5,000 tons per year, so quite typical situation for small production sites, not only at Covestro, but at many other sites. And if you incinerate that, so a typical solution for a highly concentrated liquid waste, you need to spend about 5 times as much energy. However, most of it, the energy you spend, you get back in terms of steam typically. So you have a steam generation connected with it. It's high value energy, we need it anyhow. So most of the energy you get back. However, there's a certain part of energy that you don't get back, and even worse, you don't get any of the, let's say, chemical energy which is in the waste back. If you now go to, for example, wet oxidation, which is another typical process for these kind of wastes, so you oxidize it in a liquid phase, you need to spend significantly less energy. In this case, you need to spend more electricity, but and you also get some energy back, in this case, rather low value because it's only hot water or low pressure steam. And still, again, you don't get any of the chemical energy in the liquid phase on a net balance back. The only process where you really can get back some of the chemical energy is if you apply anaerobic processes. In this case, the process concept to have first a distillation to get out of some of the light boilers. Best cases can be used as secondary fuel, so again, energy recovery. But even if not, with converting most of the organics into biogas, you really get net energy back from your wastewater waste. So you really valorize the chemical energy in your waste. For sure, if we have things that we incinerate currently, this is very pronounced. However, the same applies if we talk about our normal wastewater, which goes to aerobic treatment plants. For sure, the energy input is significantly less. You gain less energy for aerobic treatment. And even if you have the combination of wet oxidation and aerobic biotreatment, which we have at certain times because the components are toxic, even then you get some of the energy back, but net, you don't get anything back. If you go to anaerobic treatment, for sure, all the fruit juice and paper industries, etc., they know that very well, and this is why they apply anaerobic treatment process. You really have a net energy gain from the chemical energy in your waste. And this was an incentive for us because in the chemical industry, it's much less widespread to really join the project. And we are very happy that we have the opportunity and the chance to do that, because it's always very difficult if in the chemical industry you say, well, I have one idea and there's one stream and let's go for anaerobic. In our case, we really wanted to make a potential analysis. So we screened all our wastewaters globally, worldwide with our mapping tool. We applied previous studies, we made expert interviews, we selected relevant criteria. So we want to have a certain scale, we want to have multiplications, and for sure it only makes sense if you have a certain TOC. And in the end, we ended up with 5, let's say, wastewater classes that we have. And it's all mixed from our production setup. We have batch productions, wastewater and wastes. We have waste and wastewater from Conti productions. We have it at sites which are standalone. We have it from sites which are located in chemical park. And you see here the energy gain is really significant. It's from 1 gigawatt hour up to 100 gigawatt hours per year. The large ones are from our modern processes, which are not even existing now, which are only our future circular or maybe bio-based processes. We applied a lot of different technologies, maybe the partners, TU Darmstadt and Biosane, Veolia, lab tests, pre-tests, Conti tests, etc., with different setup, EGSB and membrane bioreactor and the anaerobic part. And I only wanted to highlight 3, let's say, findings from the many, many results that we have. I mean, on one hand, for sure, the seeding sludge has an influence. So if we start up our processes, our anaerobic processes, we select a certain biomass, and unlike the expectation, sometimes not the biomass from a chemical industry anaerobic reactor work best, but the one from maybe paper industry. So there are certain components in which trigger a certain adaptation of the biomass. Secondly, the batches in our wastewater, for sure, if we have batch production, if you take one batch and 1 month later the second batch, we know very well they behave different in terms of anaerobic treatment. So there's a variation in it. And sometimes even if you treat one batch at the first time, then you let the reactor run for 2 more months with another batch and then convert to the first batch. It might be that the first batch reacts much, much better due to adaptation. And this is a very important finding. We know it from our aerobic plants. You know, due to 10, 20, 30 years of adaptation, our aerobic plants are able to treat waste and wastewater much different to what you expect in a small pilot. And this is also a learning here. You really have to take the time and to allow for adaptation. And this, the time, so is not in terms of days or weeks of operation, but is of months of operation. And this is also a very important point. We are just moved in the Cornerstone project from the so-called lab phase to the pilot phase. And in our case, the pilot phase, it's not reasonable to only move to a larger reactor, or mostly not even necessary. If you have an EGSB reactor in a decent lab scale of 30, 40, 50 liters or whatever, which has all the components of an EGSB reactor, it's fully representative, and it's much more important to get different wastewater batches and to allow it to run for more half a year or something like that, than to just scale it up and then let it run for 1 or 2 months. So scale-up parameters are the time and not so much the reactor size itself. So concluding, this was my conclusion from December 25 in another talk at the Water Project Europe event. And indeed, we found that significantly more streams were promising than we expected at the beginning. At the beginning, we thought, well, if we have 2 streams in the end which are promising, we are happy. Now we work with 4 at least. This is also why we applied 2 technology modules instead of 1, which was originally planned. And yeah, very promising results. And in December, we looked around for the next step and partners. Also, conclusion from last time, regulatory requirements are really a hassle in terms of sample shipment. The project manager, Meenakshi, my gut feeling was always that most of the time she just spent on organizing that our wastewater sample is sent from A to B to the different partners and to the pre-treatment partners, etc. And this for sure means it is cost, it's effort, and mostly does not show up in the project budget because not all the people involved really make their hours on the project. And at that time I said, well, and in the end it might lead to the fact that innovation is impossible. And now if I revise the conclusion, yes, the positive side is even more positive. So the results are still, even in these 5 months, were even more promising for me. So I'm absolutely happy that we can do that project, and with these partners especially. We are already working on the next steps with partners. We have a next project collaboration. We have talks with the partners in the chemical parks. However, also the hurdles, verified and increased. And what you see here, I just asked the colleague who mainly takes care of sample shipment to put the names of all the people that are required to send the wastewater in the Cornerstone project in Europe, in Germany, sometimes from A to B. And you don't need to calculate, it's 55 persons. But I'm absolutely sure we did not name all the people there. And it's really, sometimes I think, how can we still make innovation if we have so much effort and resources only to ship wastewater from A to B? And regarding innovation impossible, yes, not in the Cornerstone project, but in another project, we wanted to use one waste from us, a European site. We wanted to try an innovative European process to treat this wastewater, to not need to incinerate it. So we wanted to contribute to the European goals into climate neutrality and circularity, and we failed. After 1.5 years of applications into regulatory stuff, we failed, got the final declining of the relevant authority that we allowed to send 1 tank truck of wastewater from country A in Europe to country B in Europe. And it's not the one regulation that hinders us. You know, it's a whole bunch of regulations which I'm not even aware of. I mean, we at Covestro, we have a department that takes care of all regulations. And then we go to them and say, we want to ship wastewater. And then they have a whole list of things we need to do. And this is really, for me, the first time where really innovation in this case was simply blocked by whatever regulation. I don't know which one it was, but I wanted to take the chance at this talk to highlight that we must change something. Otherwise, we will not be innovative anymore. But we also have the green side. don't take care. So very promising results in CORNERSTONE. Yeah, thanks.
Yes, thank you, Christoph, for this nice presentation. And it's always good to hear from the industry what is working good, and especially also what is not working very good. And the shipment is for sure a challenge. So this was the chemical industry we have in CORNERSTONE, and now we will move to the steel industry case. And here we'll have Pavel Ivashikin, who is Deputy Head of Department at the BFI Applied Research Institute. And in the CORNERSTONE project, he is the coordinator of the steel industry case study. So please, Pavel, if you can
All right.
present.
Thank you. Thank you, Chesna, for the introduction. Yes. I'd like to present the steel case study. So our Applied Research Institute, BFI, works mostly with the steel industry in Germany and Europe, and we try to optimize the steel production processes, also involving the water side. So the result of cooling water used in the steel industry, as you can guess. So and I'm going to show you to what are the current possibilities to use the resources that are in this water, which is the heat, water itself, and the solute, and how we could recover it. So currently, the steel industry faces a huge challenge to achieve climate neutrality till 2050, because, as you know, steel is produced from iron ore using coke. So basically, it's a CO2 production plant rather than steel production plant. And to change that, coke will be replaced by hydrogen. And the first plant's already been built in Germany, at least. And so what happens in this case is that the current gas temperatures from about 150 degrees in the blast furnace will rise up to 500 degrees, leading to the huge temperature increase in the water up to 85 degrees, and the huge amount of heat that is currently planned will be transferred to environment via the cooling tower. So we're talking about 100 megawatt power for a single plant. So the circuit is pretty simple. So from the scrubber, the hot water would go to the sedimentation tank and then to the cooling tower. And we have some blowdown, and we have some fresh water that we need to make up for the evaporation losses and for the blowdown. And the cornerstone concept is to use this waste heat at 85 degrees to power membrane distillation to treat the blowdown. And then we can recover the solute by bipolar electrodialysis and recover the water, which we can use to supplement fresh water demand, and or use for hydrogen production by electrolysis, closing this circle for hydrogen powered direct reduction. The challenge is that in this process water there are suspended solids which are blocking the normal plate heat exchanger within 2 days. So in the cornerstone, we are developing non-clogging heat exchanger that could look like this. So there's a spot welded heat exchanger plates with spacing of 60 millimeters instead of 5 millimeters that you have in a standard heat exchanger. And this kind of block of these plates could be installed in the
in the channel of gas carbon waters, for example. And in order to prevent the precipitation on the surface or blocking of the channel, we also applied ultrasound. So as we didn't have access to direct reduction plant, we first tried with a gas carbon water channel of blast furnace. And you see on the left side that we had quite a layer. After 20 days, we had around 8 mm layer, and the heat transfer reduced by 90%. And actually, already after 5 days, we had only the half of energy we could recover from that. So in that case, ultrasound didn't help. So we need stronger ultrasound or need some other cleaning, either by nozzle, like water stream cleaning, or by some mechanical part to maintain the heat transfer we would like to recover the heat. Also, for the gas carbon water of basic oxygen furnace, we tested that, and in that case, the drop of the heat transfer coefficient was not so dramatic, but it did decrease over time, and there was no stop to the tendency. In that case, ultrasound helped to maintain, to stabilize the heat transfer at the 55% of the initial, which was a pretty much okay result for the industrial application. The tests were done in real gas carbon water channels, so we had realistic conditions, and we also saw that the layer of carbonates when we were using ultrasonic treatment was thinner than in case of a normal operation. So there's a positive results in the application of the heat exchanger. Now the question was, what do we do with this heat? And we wanted to power the membrane distillation with this heat. In that case, we used vacuum membrane distillation with a technical plant that can produce up to 200 liters per day. And we reached the stable flux of 6 liters per square meter an hour with a thermal energy demand of 200 to 250 kilowatt hour per cubic meter, which is much lower than for direct contact membrane distillation. Had a water recovery rate of 76% and very low conductivity in distillate when we were using synthetic salt solutions. But in case of real gas carbon water, we had the higher conductivity of, let's say, 7 to 10 microsiemens per centimeter, which was due to the presence of ammonium. But even then, the distillate could be used to substitute freshwater demand, and for hydrogen production, additional treatment would be needed. So, to summarize all that, we see that the tendency, the new plants that were built for hydrogen-based direct reduction of iron ore, they offer high chances for sustainable water and solute recovery from the gas carbon circuit, and the temperature level of 85% can easily power membrane distillation. But the waste heat recovery is challenging due to the suspended solids content, and the heat exchanger that we're developing is going to manage this challenge. So membrane distillation itself reached very high quality distillate at considerable distillate flux and comparably low thermal energy consumption. So We think that in the next 1.5 years that we have till the project finish, we will make long-term tests with ultrasonic techniques or nozzles to maintain the stable heat transfer over 50% of the heat transfer capacity of the heat exchanger. And yeah, we will also test the further preparation of further treatment of the water till to make it as feed for hydrogen production. Thank you very much.
Yes, thank you, Pavel, for this nice presentation. And I think this was the final of the Cornerstone presentation.
We now move to the guest project MEloDIZER, which focuses on sustainable membrane distillation for industrial water use. I'm pleased to introduce Matteo Fasano, Associate Professor at Politecnico di Torino and Coordinator of the MEloDIZER project. Matteo, the floor is yours.
Okay, good morning to everyone. I hope you can hear me well and see the screen. So thanks for the introduction and for the invitation. So today we represent the consortium of MEloDIZER projects, which stands for Sustainable Membrane Distillation for Industrial Water Use and Decentralized Desalination Approaching Zero Waste. So this is an overview, just a few data analytics about the project, which started in 2022, so it's going to expire and end quite soon. So we are actually at the demonstration phase. So the consortium is made of industrial partners that are mainly the end user of the technologies. We have 4 demo sites to demonstrate membrane distillation for wastewater treatment and also for desalination application. Then we have some universities and small medium enterprises that instead help it synergistically to cover the scientific aspects and also the scale-up aspects of these technologies. So just even if for sure now it's quite clear the technology after all this presentation, just an introduction, a generic introduction about membrane distillation, which is a technology that treats a old salty feed on one side, and then the heat can be taken from some waste heat or from renewable source. And on the other side produces a cold distillate stream, thanks to the presence of a hydrophobic membrane that allows the vapor to flow through while blocking the liquid part. This is a configuration in direct contact, but of course, as was shown earlier, many other configurations exist and have been also explored in the project. So the idea is to exploit the temperature gradients available, better if it is available for free, let's say, because you have some waste heat, to overcome the salinity gradient and so the activity gradient, and so to obtain a net vapor pressure from the feed water to the permeate. And so the driving force is the difference of the vapor pressure that you obtain. This is particularly helpful for feed waters with high salinity, which should not have, in principle, volatile compounds that can go together on the permeate side. And so some pre-treatments are typically needed to make the water to be treated adequate for this type of technology. In our projects, we have a few specific objectives. So first, we focus, since our call was quite focused on the membranes, we focus on next generation membrane for membrane distillation, hydrophobic membranes that should be more sustainable, meaning that the solvents adopted for the synthesis should be replaced with greener solvents, so that then can be scaled up with a low impact solution. And the second aspect then is integration of the membranes and then the modules that are built upon with energy and control system to optimize the thermodynamic and economic performance of the system, always keeping an eye on renewable sources of energy or waste heat, and then demonstrate these systems into some relevant case studies of industrial waste streams and in our case also for the supply of drinking water for decentralized desalination application. And then the last but not least objective is also to quantify the economic and environmental benefits associated with these technologies, thanks to some LCC and LCA and market survey analysis. So the implicit, let's say, challenges and objectives of the project is really to take the best out of this membrane distillation technology in the different configuration and shapes that have been also presented earlier, that of course can be tailored for specific feed water and specific energy supplies. And so the idea is, at least for these 4 case studies, that then have some also other wastewater that can be treated. For these case studies, really to check if membrane distillation can be inserted in some water treatment trains, and if yes, how, in what is the best way to do that. And so exploit this intrinsic flexibility of the membrane distillation technology to, for some case studies, improve the scalability of the technology up to TRL 7. And in our case, we also have this important aspect to compare how membrane distillation can be used in some cases to have a decentralized, portable, passive and low-tech system to supply drinkable water in case of emergency condition, versus instead more sophisticated industrial scale technologies for wastewater treatment. So this is the overall approach. The project start analyzing membrane science and synthesis and characterization. Then we have an engineering part related to module building and system assembly. And finally, we have demonstration in real industrial environment in the 4 demo sites, both for water reuse, resource recovery, and desalination. And transversal to these approaches and activities, we have a multi-scale modeling activity on top of LCA and LCC analysis and social impacts. So just a very brief overview of the main results. We analyzed both flat sheet and hollow fiber membrane technologies, and for what concerned the chemical part, our partners were able to obtain membranes using either solvents which have a lower ambient environmental impact, or environmentally benign, so without any trouble, coatings that allows to extend the lifetime of the membranes if they are applied on commercial membranes. And this is one example of the membranes produced and the modules generated. And this was obtained at the lab scale, and then the industrial partner upscaled the production of these membranes to tens of square meters of production that was needed for the demonstrator. For what concerns the hollow fiber, the analysis here focus more on the synthesis part and not on the coating part. And in this case, the use of a more sustainable solvent was optimized in order to get comparable performance with commercial membranes. And also in this case, the industrial partner scaled up the production of the hollow fibers. For the modeling, this was a multi-scale modeling, so there is no time really to show everything, but we focus at the membrane scale to optimize the composition and porosity and surface feature of the membrane for some specific boundary condition. Then we model by fluid dynamics, basically the module. And finally, with lumped element approaches, we approach the water energy integration systems and control system of the demonstrator. So for what concerns the demonstrator that are now all designed, and some of them are in production, some of them are already installed. For what concerns industrial wastewaters, we have the demo, let's say number 1, which implement direct contact membrane distillation with hollow fibers. The target production is 2 cubic meters per day, and so we have 20 square meters of membrane. So here the idea is to recover waste heat from spent grains from a fermentation process of a brewery. And this waste heat is very abundant. So we're talking about hundreds of megawatts at low temperature. plus possibly some auxiliary system are used to concentrate the wastewater and also to recover potentially some helpful materials out of it. And we test, of course, the brewing wastewaters from the process, but also we ship some aquaculture waters from our partner in Malta. And so these are just some picture of the system that is under construction and will be finalized in July. Then we have a second demonstrator, which instead implements vacuum membrane distillation, as was explained in the previous presentation. Here we test instead flat sheets. The target of water treatment is a little bit lower, so alpha cubic meter per day. So we can really explore different scales also in the terms of production. These are the square meters of the membranes we used. Here the concept is not to explain waste heat, but to explain, to exploit the electricity generated by a PV system, thanks to a heat pump that can then produce available heat, low temperature heat. This is particularly helpful, particularly in highly electrified networks and highly renewable networks like the one in Spain, where the demonstrator is installed. And here the idea is to treat waters from chemical process and also textile feed waters. And the target here is not for material recovery, but rather for concentration of the feed. And of course, the process comes from after a train of pre-treatments of this wastewater, for example, reverse osmosis. This is an overview of the demonstrator and the different components that are available. So in this case, we also have some thermal energy storage device to optimize the performance of the heat pump. Then for what concerns the desalination, we have two additional demonstrators. In the demo number 3, the concept is air gap membrane distillation in a different fashion. So on top of the bulk heating by some solar thermal panels, we also have direct solar heating on top of the feed water side. And this, we have shown that dramatically increases the performance because it reduces the temperature polarization effects in the module. So the target here is a little bit lower, is in the range of 100 liters per day. And here the idea is to exploit renewable heat and also to exploit this new, scientifically new configuration where the solar heat is directly deposited on top of the feed water side. The demonstrator is installed in Spain at PSA, Plataforma Solar de Almería. And finally, we have a different concept, which is an emergency kit exploiting air gap membrane distillation and flat sheet membranes that should be very portable, lightweight, easy to be used by citizens with a small size and also a long shelf life. So you should keep in your wardrobe for years and then use it whenever the main source of drinkable water is compromised by some natural events or other disasters. And so here the idea is to exploit solar heat that is available everywhere, let's say. The performance, of course, decreases, but the good point is that also the cost decreases and also the system is thought to be portable and easily assemblable and usable by citizens without any control logics, but then can operate in a passive way. And here the demonstrator site will be in Eilat using sea and brackish water and will be tested by citizens. So this is an overview. And so as you can see, we test different feed waters, industrial and desalination, and different membranes, modules, and productivity. So we could really explore different aspects of membrane distillation. And just to conclude, all these analyses are always supported by LCA. And in particular, was particularly helpful for the solvent screening, so to identify suitable chemicals available for solvent and so to produce more sustainable membranes with both low environmental impact, lower toxicity, and at least the same functionality than state of the art. And also the LCC helped us to reshape the manufacturing step of the modules and to extrapolate how the cost would scale down if then scale production will be generated. And clearly also for the desalination part, so for the part related to the citizen interaction, we are conducting also social acceptance to really understand if people would be fine to drink this distilled water in an emergency condition. So that's it. I thank you very much for the attention. Here you can see a picture of the consortium from the initial ideas, initial meetings up to the final demonstrators that are being installed right now. Thank you.
Thank you very much, Matteo, and thanks to all the speakers. I mean, for this exciting and striking presentations of the projects. And I do hope that there will be, next opportunities. I'm confident there will be additional opportunities for this kind of discussion between all the concerned projects that are working on industrial water circularity. Now, we move to the panel discussion. As you know, we have a panel discussion that it is made in order to help to connect the different project perspectives that are being presented today, and to explore also common challenges. This is also the way that we see, the declaration of the synergies and the opportunities in order to work, on better chances for increase the capacity of the industrial sector in water, and not only water circularity. So I'm pleased to introduce the moderator of this session, which is Małgorzata Szafra from the Tampere University, and she plays the role of co-leader of the Water Europe expert group on the resource recovery. And but let me also highlight the matter that in this panel we have also a participation of A.SPIRE, which is an additional guest. Is not a project in the panel discussion, but it is a water rental living lab. And the reason is bringing the perspective of real life environments as water rental living labs could be in this exchange of today. A.SPIRE is part of the network of the water rental living labs that Water Europe coordinates in the framework of the European Union co-funded partnership Water for All. Thank you so much also for what is coming in the next session. And Gosia, the floor is yours. Thank you.
Thank you so much, Andrea. So we just heard how these excellent projects address industrial water circularity from different angles. And in this panel discussion, maybe a few words of the explanation how it will go. I will direct my questions to the project coordinators, and then you may pass them to colleagues from your consortia. And we will do 2 rounds and then turn to audience. So to everyone watching or listening, please feel free to add your question in a chat box at any point, and we'll get back to you, to your questions after the second round. So let's begin then. And so as we already heard and learned from your all presentations, your projects share the same ambition, so turning industrial wastewater into the valuable resources. But each of you takes a different approach to get it there. So my question is, which approach or result outcome from another project would you like to bring into your work, and why? And maybe, Shufei, can I start with you, please? So what would you like to bring from the RESURGENCE?
Yes, well, thank you, Małgorzata, for the question. Well, for example, from a revolution, well, the content I find very interesting is not from today's presentation, but in the last event. The fact they are using digital twins to support the application of solutions in different scenarios. Well, in RESURGENCE, we are also developing digital tools, but every case is built on the experimental validation results. So I think both approaches are complementary. One is very useful for transferability and scenario testing, and while the other one is connected to validated technology performance. This is something we could further learn from and exchange on. And from Cornerstone, I like the fact that the treatment modules are defined for each case, which allows a very focused development and demonstration at the case study level. While in Resurgence, our approach is slightly different. We developed several similar but also technically different innovative technologies, compare their performance, and then select the most suitable treatment train for each industrial case. But this gives us, this in one hand gives us flexibility, but it also makes the selection and integration process more complex. And what MEloDIZER is a new project for me, and I learned a lot from the presentation today. And I find that they are not just testing membrane distillation as a process, but also improving membrane modules and energy integration, which what we can learn from is how to go deeper into optimization of one specific technology to deal with difficult streams.
Thank you so much.
All. Yeah, thank you.
Thank you. And then, Lydia, the same question to you. What would you borrow and bring to the revolution, and why?
So I find really interesting the way heat recovery is implemented in Cornerstone, because most of the other projects, well, all the other projects rely on membrane distillation and some kind of heat recovery with heat exchanger, heat pump, or other technology. But in Cornerstone, this is done differently. So they rely on biogas production. And I think this is interesting. This could be interesting, for example, for the biochemical case where they have also high organic production. So this could be implemented. So I think this is another point of view of how heat recovery could be implemented in the industry.
Yes, indeed. Thank you so much. So, Czesna, what about from Cornerstone side then?
Yes, thank you, Margosata. I think from Cornerstone, I can say that we develop these decision support tools, and what I see as synergies between our projects is that we have different companies involved in the different projects, but it's the similar industries. So again, this discussion with the industries can really be valuable for developing these tools. And also as an additional thing with the MEloDIZER project, that they are ahead of us in terms of piloting and demonstrating the technology. So there is for sure also some knowledge here in how we scale up and demonstrate the processes. So this is what I see from our side.
Thank you so much. So Matteo, you've got a fresh eye on all these three sister projects. So what would you take from them?
Yeah, so I mean, as a mechanical engineer, I particularly appreciate the investigation in Cornerstone about the heat exchangers, because also this was this seems to be a side problem in our demonstrator sites, but eventually it came out also to be one of the major project of problems of integrations of our membrane distillation technologies with the the spent grains from the brewery. The system initially available was a tube-in-tube, basically, but it had a lot of problems, both in terms of fouling and also in terms of mechanical issues. And so, knowing before, or maybe in the future, using instead some other technologies, I appreciated this investigation braided exchanger, specifically tailored for this type, for other types of feed waters, but I think also something similar could be done with the brewing company. I think is a very important aspects in the integrated system of waste heat recovery for membrane distillation. So, it's not really a side problem, but if you really want to do something with waste heat, then it gets very important to redesign existing heat exchangers. So it's a really important problem.
Thank you so much. It seems that we can learn from each other a lot and borrow and adapt to your projects. So now let's go a little bit to the harder question. This one was easy. So we've seen that in your projects, of course, technologies are tested, working for the real industrial settings. And so can you please tell us, what are they already standard practice? But if not, whose responsibility do you think is to change that? And Dimitri, because thank you so much joining us today. We are really appreciate this. So can we start, please, from you? I would like to start this second round. What do you think? What is really holding this back?
Well, you're practically asking about the barriers of breaking one technology to the water industry. So I'm going to start by saying that barriers are usually multi-parameter problems or multi-stakeholders, if you want, and they command a multi-stakeholder solution. To start with, we have the economic or financial barrier, where usually it's the acquisition or maintenance cost of a technology. And here's where the technology provider should give enough value through the technology to the adopter. And on the other hand, the adopter should not just judge the short-term gains, but to see the long-term gains and how this technology can help the sustainability and resilience of the industry. Another barrier is governance. And do local authorities facilitate the technology, or do they hinder it? I mean, this is very difficult to answer to this, but it seems to be very local. In different regions, different local authorities behave in a different way. Another important factor is the acceptance by society. And of course, the public needs to be educated by the technology providers, academia, the authorities, and so on. But also today, as citizens, we cannot maintain a passive stance toward technology, and we need to go beyond consuming it. We need to seek for it and guide it and demand it, get more involved in it.
It's a very good point, but I have one more question to you. Do you think so, because we are working academic combined with the industry, do you think so that the ownership is the issue or not?
Great question. Ownership in terms of equity or in terms of being involved?
Equity.
Equity. Yes, ownership is a big problem. And this is why we have invested a lot of time in developing a business model where we try to move ownership out of the equation of adoption. So we offer the technology as a product as a service. Rather than selling it, we make it available, we lease it to the industry just for the amount of time they need it. And this is also particularly convenient for industries like the food processing sector that that do not work continuously throughout the year. So they can only use the technology for as long as they need it. 3 months a year, 4 months a year, it doesn't matter.
Thank you so much. It's always very nice to see and listen to the perspective of the industrial part. Thank you so much. Czesna, do you see it the same way? You already, your consortia expressed some opinion on that.
I really agree with what Dimitri is telling, and it's really multi-stakeholder issues here. And I think also one of the things is that, for example, in these projects, we are developing to TL6. So it's still in the demonstration. I think MEloDIZER is maybe a bit higher, but it's still in the demonstration phase. So for the further exploitation of the technologies, again, it's integrated approach, but who is going to take the risks about the further commercialization? Is the technology providers? Is it the industries that it will implement it? And how we have the opportunities now is that it's difficult for the industries maybe to go and take the risk that they will implement some technologies where we do not really know the true outcome yet, although we have demonstrated and it's working well. So I think it's a lot about who is taking the risk. If you have to apply for funding, it takes a long time to get the answers. It's the success rates are very low. So I think that is one of the reasons that many European projects they end somehow, because there's this gap between our projects and then the next levels. It's about who's taking the risks.
Yeah, thank you so much. Yes, a very good point, very good point. And Lydia, what is your view here?
So following the speaking of Seshna, I would like to add that maybe if the companies will have some incentive for recovering heat and water and resources, they will take less risk. So this could be a possible solution. So for that, regulations have to make to catch up with the reality. But if not, I think the companies, if the business case is not clear, the companies will simply keep moving, paying for fresh water and energy and throwing the rest away.
Yeah, thank you. And we are going to Shufei, to close the round here. What do you think about that? Do you have something to add?
I agree with all the previous speakers because I think the responsibility here is shared. I'm not going to repeat all the thoughts, but I think as a researcher, I could add as researchers, we could, besides being focused on developing our technology, carefully monitoring every parameter, and wish the technology to be perfect, we should think out of the box a little bit to think that the technology should be scalable, should be easy to operate and economically viable, to be ready to share the technology with industries.
Thank you so much. We are a little bit behind the schedule, but before we move further, let's give a chance also our audience, and let's check what is coming from them. So over to you, Isabella. Do we have any questions from the audience?
So we have a question for Resurgence. What kind of a membrane material is used for membrane distillation? And what is the decision behind stopping at water recovery factors around 40%?
So
Well,
I think
yes.
yeah, please.
No, please, yeah.
Okay, sorry, because this question I think is directed towards what I presented. Quick answer for the type of membrane that we were using was a commercial PTFE membrane. So it was commercially available, 0.2 micrometer size. And regarding the water recovery, I mean, the only decision to stop around 40% was owing to the limits in the laboratory. We wanted to be able to compare all the waters, so we decided to operate at 3 hours and compare all the waters in that time. If we did longer operation times, I believe the water recovery will be a little higher. Thank you.
Thank you so much. So, Isabella, anything else?
Yeah, I think if you all agree, I will hand over to Shufei to close the event.
Yes, thank you so much. Thank you all.
Thank you.
I think there is a question from one of the attendees. I don't know, it's Lucia Saya. I'm not sure if there is a question still, but
I cannot read it. I cannot see in the chat.
I see it's she has raised the hand, and it's Lucia Saya.
Lucia, can you hear us, or you can put your question in the chat box, or just yes, yeah, please. Can we please go ahead?
I think she
no,
put hands
yes,
up.
no,
With,
no
yeah.
questions from her side. Thank you so much. Okay, over to you, Isabella. Thank you so much.
So please, Shufei, the floor is yours.
Yeah, thank you. Well, since we are already a little bit late of time, I would thank all of the speakers, the moderator, and the audience for joining today's event. I think this discussion has clearly shown that the industrial wastewater is no longer only a waste stream to be treated, but a potential source of water, resource, and energy. And I think one of the most important message from today is the need for collaboration and knowledge exchange by sharing the results, the lessons learned, the barriers we found, and the successful approaches. We could broader replicability of our strategies. So I'm not going to be long. Thank you again for everyone. And this is our third clustering event. I hope this event will continue for further exchanges and future synergies between our projects once we have more demonstration results. Thank you. And also thank you for the organization from Water Europe.
Thank you so much.
Thank you too.
Thanks.